lecture, which is our lecture on the nature of light, which will be given by Professor Hasan on the nature of light, right? So I will move off and we'll start with that. Sure. Just which is our lecture on the nature, which is yeah. So 1 sec.
Make me a co-host.
It's recording.
Maybe I have to start my presentation.
Stop the light.
Yeah. Did you switch on the mic?
No. Open it now.
So, good morning, everyone. I'll give you a more basic talk on light, and I assume that there are a lot of students in this from school, and hence we'll get down to the bare basics of it and see what essentially light is, and then we'll use what we are going to see to do a few demonstrations, simple ones, which can be demonstrated in schools or it can be done at home or so on. Yeah, so what is light? Yeah, we see light all around us. We get light from the stars, we have light to the signals, we have an electric bulb, and we have these beautiful aurora borealis, which are discharges which we see in the northern and the southern hemispheres. Beautiful light streaks which we see. So what is light? In a very basic way, we could say it's the form of energy which is detected by eyes. Right? And we'll go a bit ahead later and define it in a more rigorous way. But basically, what is light? Light is something which stimulates our eyes and we get to detect it by eyes. And that's what makes it, that's what we call as light. If our eyes don't detect it, then that form of energy is not taken as light. So here we have two pictures. There could be many more. We have the sun, which is the source of light for Earth. And we have an electric bulb, which we have the source of light when sun sets. And in our homes, we light all kinds of incandescent bulbs or discharge tube and so on, right? And the question is there a relation between heat and light? Because when we see any source of light, let it be a bulb or the sun or anything, if you feel it, it feels hot, right? So is there something with relation between them? And what we shall see is, yes, there is a relation between them. and it's an important relationship. Yeah. So if you realize, as science has progressed, people have gone from a very complicated model of the world, of the universe, to something more simpler. Earlier, everything was a different form of energy, right? Light was different, heat was different, electricity was different, magnetism was something else, gravity was something else, and so on. And slowly we are moving towards a unification. What we have reached as of now is we have realized that heat, light, electricity, magnetism, these are all one and the same. Things which you detect by your eye is what is light, and things which you detect by an instrument which measures heat, say a thermometer or so, is heat. And we will see that in fact electricity and magnetism are also, these are all electromagnetic waves. And science has progressed further, and we have also, so right, there was a stage when everything was a different form of energy, but then we came down to a stage where there were only four forms of energy: electromagnetism, strong forces, weak forces, and gravitational force. Then there was a time when work demonstrated that weak force and electromagnetic force can be united. And these are called electro-weak force. So we got reduced to three basic forces of nature. And once this was done by Abdus Salam and Weinberger of uniting electricity, magnetism, and so on, we further went and realized that the strong forces too could be united. So now the only evasive force which we cannot unite in the same spectrum is gravity. But there are efforts being made where they are trying to get the grand unification theory, or theory of everything two, or guts, and people are trying to come to a very simplified model. So we shall not go too far. We'll just come down till light, because that's the purpose of today's talk. And this phenomena associated with light, which we are familiar with, we have reflection, refraction, diffraction, interference, and so on. And then we also notice that light has different colors. You have red, blue, green, and so on. Okay, so coming to what is the nature of light. From time immemorial, people have been trying to understand what light was, and light is essential because we see things. If there was light, and if there was no light, then we wouldn't see it. And there are a lot of antiquity theories which said what was light and how do we see. People earlier thought that our eyes emit certain particles which go and strike objects and they bounce back, and then we observe that object. So something is emitted from our eyes. But then there were others who said, no, it's the other way around. There are some particles, energy particles, which are being emitted from these objects, which reach our eyes, and we process that. In fact, Ibn Haytham, an Arab mathematician and a physicist, he further went and said that, yeah, the second thing was right, where the light photons from objects, they enter our eyes, and it's processed in our brain. It's not the eyes which see it, but the image is formed, and you see things through your brain, right? So, and he's the father of optics. Coming down to the basic nature of light, Newton, famous Newton, who spoke of gravity, who has done wonderful work in physics, they laid the foundations of mechanics, which makes us understand why bodies move and what are the basic laws, which also explain why the solar system is held together and why planets go around the sun. Newton has done tremendous amount of work on light as well. Newton believed that light has particle nature, and Huygens, who lived at the same time, and his associates thought light was a wave. It propagates as a wave. Okay, so Newton had this corpuscular theory of light, while Huygens and all had the wave nature of light. And Huygens and others said that they looked at the scattering of light in glass, right? If you have light falling into a glass, they said it gets dispersed, and the glass distorts the properties of it, and hence, since it's a wave, as it goes in from one medium to another, it spoils its properties, and hence the light splits into the spectrum. While Newton explained it in 1666 by using prisms, and he connected them in this way and showed that you can recombine white light, which breaks up into the spectrum, and then you can reunite them back into a light. So Newton strongly believed that there are particles which carry this information, and Huygens and others felt it's the light has wave properties. If you look at reflection and refraction, you take any mirror and you shine a light on it. You see, you can explain it very well as balls bouncing back, right? So if you use the particle nature of light, the reflection and refraction can be very well explained. And here are all these ray diagrams which show how you see an object in a, say, a plane mirror, and how the image is formed as far from the mirror as the object is in front of the mirror. Then you can have these parabolic mirrors, and it shows how rays of light, parallel beams, can get focused at the focal point. And so the particle nature very well explains reflection and refraction. And we can draw all these beautiful ray diagrams to show how the magnifying glass works, right? So I have concave lenses and convex lenses, and it explains very well how things get magnified and so on, right? So all of us have played as kids with these objects, and we can show how things get enlarged and so on, right? And these ray diagrams, simple diagrams, which you can draw using very beautifully, can explain how objects can look bigger, or they can make it look sharper, but right. And what is refraction? Why does refraction happen and so on? But there's this other phenomena, for example, diffraction or interference, which we should see, which typically show the wave nature of light. So what we have here is a parallel beam. We have a laser which is creating this wave light front, which are parallel rays coming, and you have a barrier here, a screen with a small hole in it, and as it goes through it, you have this being created, and on a screen you can catch it, and you get a lot of intensities of bright and dark bands, which gives you the diffraction pattern. We shall see this as we proceed a little ahead. And if you change the size of the hole, make it wider, you'll see that these patterns which you get are different. Now in the same screen, if you, instead of having one hole, we have two holes in it. And as this wave front comes and hits it, these waves are created, and from the other one another wave is created, and they interfere with each other, and you will get this kind of an on a screen diffraction band. And strangely, if the source of light is, if you notice here, if you draw a line straight through this, if I draw a line straight down from here, right in front of the hole, the point somewhere here, I'll just take the spotlight. And you will notice that if you see the point right here, you are getting a dark band. We are not getting a bright one here. You would have expected that if there were particles, then right in front of the hole, you should have maximum light. But what you see is you get a dark patch here, and you are getting bright points which can be even shifted away somewhere else. There's no hole here, but the point in the screen, which is totally covered, there's no light coming from here, but you are getting bright bands here, and dark bands, they can also happen to be right in front of the hole. So this is showing it's something like a wave. As it's moving out of the wave, the two waves interact. This can be done very easily done in a tub of water, and you create a disturbance, and you have the wave moving on, and you create another one, and you see how the two waves intersect. When the two waves join in constructively, you get a bigger wave, and sometimes they go against each other and kill it, and you get no wave or a trough. Right, so this typically, in my previous slide, we saw that the particle nature very well explains reflection and refraction. But this diffraction or even interference is better explained when we consider light as a wave rather than particle. So if you have two waves and they constructively join in, you get a wave where the crests become much larger. They join in together. Even Priya was mentioning in her talk. And if the waves join in destructively, like the peak of one coincides with the crest of the other, they can cancel other, and you can have the destructive interference, right? And like Dr. Priya showed, that there can be a variety of these things where they needn't exactly kill each other or exactly get added up, but there can be many in between stages too, where they're partially right. So this very typically shows the wave nature of light. Yeah, so how do we see light today? What is the nature of light? Today we realize that it has both a particle nature as well as the wave nature. So this is called the wave-particle duality. In fact, whenever you study phenomena at a very small scale, at the quantum levels, which was mentioned in the previous talk, then you will see that these things, at the atomic level or subatomic level, when you look at electrons and protons or photons and so on, you see that they have a dual nature. You can consider them as both particles and also as a wave, right? So they are small packets of energy which have this.
Yes. Yes.
This basically gives us the wave particle duality. And what it goes to prove is both have been right. Newton was right, and so was Huygens. So light is also a particle and also a wave. Right. So we will see how these prisms, if you shoot a beam of light into it, you get it breaks up into a rainbow, and uh, you see the rainbow coming up. Okay, so you have to, yeah, we'll do it in our next session, but essentially we'll do things with this. And the another way of creating the spectrum is by using a grating. That is, you see, we have these are these gratings which we shall do in our next session, and we'll see how this again creates when you shine white light onto it, it breaks up into a spectrum, right? And other than that, there's yet another way of doing it. You can use, say, a CD or some such, and you shine light on it. And there are so many different, if you notice, you'll see a rainbow on it if you look at it at different angles, right? So you are scattering it. And what is happening is this white light is made up of many components. And as it goes from one medium to another, the different wavelengths of light, they get dispersed by different amounts, and hence it breaks it up into a spectrum. Yeah, we should see this as we proceed ahead. So now, what is the importance of light? I needn't specify that. Yeah, if we are teaching in school, then maybe it can be a good idea to let the children say what is the importance of light. And right, then things are very obvious. They'll come up with, if there was no light, we would not see anything. The whole universe would be dark. We won't see the stars. We won't see the sun. Even if the sun was there, and suppose it was not emitting light, it was emitting heat, but no light, then obviously photosynthesis would stop. The plants would not create food, because it won't be available for us, and probably that could lead to an end of life. But few people may argue that there are other sources. For example, mushrooms. Mushrooms will grow even without light. So suppose there was no light, you switch off light and you see what the universe would look like. And we can't rule away right away that there could be no life at all. And even the life which we see on Earth will still survive for some time, and ultimately even that would die off, right? So you can encourage students to think on those lines and see how far they can go. Okay. Other questions which we can ask is, what if reflection is switched off? You know, that phenomena of reflection doesn't happen. Then what would happen? So one thing, if reflection is turned off, then yes, I will not be able to see myself in a mirror. In fact, we will not be able to see anything. Yeah, suppose the light is there, the sun is on, or there's a bulb and there are stars and you are receiving those lights, you can see them. But if there was no reflection, then we would not see the moon. We would only see objects which are creating their own light, like the light bulb or the algae and the sea, which have some kind of chemical reactions which glow in the dark. There are certain fishes, creatures which emit these phosphorants. All those things can be seen, but everything around would be dark, because when you are seeing me now, I'm not emitting light, I am just reflecting light. So if reflection is gone, then even with light switched on in your room, you will not be able to see anything. Everything would be in darkness, right? This is a realization which the children should realize that reflection is not only reflecting from a shiny object where you shine a light and it shines back, and but the light which comes, falls, and reflects back is essential for us to see things around, for us to see the plants around, the building, you and me, and the book will not be able to read if there was no reflection. And yes, the next question can be, what if radiation is switched off? There is no radiation. Yeah. So now, what is radiation? Coming to heat, I've said there's relationship between heat and light. So heat, we have studied in school, gets transmitted in essentially three ways. You have conduction, convection, and radiation. In conduction, it happens in solids, where you take a rod and I start heating it, and the other end of it becomes hot. So the heat is transferred in solids to conduction. In convection, where you have fluids like in water, you start boiling it, or milk or air, the lower layers get heated up and the convection is set up and they carry heat around. And the third form is through radiation. So essentially, the heat which is coming to us from the sun, which is the source of life for us, is through radiation. There is no solid connect between sun and us. There is no air also, or any kind of liquid between the sun and us. So between sun and the earth, there's almost a vacuum. I wouldn't say it is 100% vacuum, but it's almost a vacuum. The number of particles in spaces between sun and us is extremely, extremely diffuse. So it's not the convection which is getting it, but it's the radiation. So the third form of energy, transfer of energy is through radiation. So if light was switched off, then we would not, the whole earth would be dark. But if radiation is switched off, then even the heat from the sun would not reach us. And that could be, everything would freeze, and ocean would freeze, we would freeze, and in no time, everything would end. Right? So it would be interesting to see how you can encourage students in school to explain what radiation is and say that what if radiation is gone, or what if reflection is not there, what if a certain thing is, and it can go on, and you'll realize that there are so many things which are related and absolutely essential for life survival. So now coming a little ahead, when we are looking at the stars, what do we see? We see they are of different brightness and they are of different colors, right? And what is brightness? Brightness, we call them luminosity, and luminosity depends on two things. I'll go a little ahead. Oh, I think some slides are not showing up for some reason. Just a minute. Yeah, some slides were hidden for no reason at all. Yeah, so in fact, I was missing out. Yeah, so defining what light is it is an electromagnetic radiation that can be detected by the human eye. And electromagnetic radiation occurs over an extremely wide range of wavelengths, from gamma rays, whose wavelengths are very small, which is about 10 to the power of minus 11 meters, right? So 10 to the power of minus 11 means 0.00000 11, and 1, right? 0.1 is 0.1, 10 to the power of minus 2 is 0.01. So 10 to the power of minus 11 is 0.000, 10 zeros and 1. Right? So extremely small wavelength. And radio waves, they go in meters. And right, so they are large, meters and kilometers. Okay. And the light, visible light, which we see is a very small part of the electromagnetic spectrum, which we see here is what our eye detects. And this part of the electromagnetic spectrum is what we call light. Okay. So when the wavelength of light is small, the energy is high. You have gamma rays, X-rays, ultraviolet, right? So as you are going from gamma rays to X-rays, the wavelength is becoming larger, and the energy is becoming bigger. And as you go from left to right, your wavelengths are becoming large, and your energy is becoming low. Okay, and our eye can detect only 400 to 700 nanometers, and that is what is right. So in fact, if you take a spectrum and you get a spectrum here and you put a thermometer, you will see that the temperature keeps changing when you put it on the blue one, red one, green one, if you have a sensitive thermometer. And when you go beyond the red, you don't see anything on the screen, but if you put a thermometer there, you will see a rise in that. Similarly, you go beyond blue, your eye will not be able to see it, but there is some radiation coming, this electromagnetic radiation, and you put a thermometer and you see there's a rise in temperature. Okay, so color of light is essentially the wavelength. Larger wavelengths of visible light are the red ones, and the shortest wavelength which an eye can see is the blue one. So what color is essentially its wavelength, and wavelength, or you talk about its energy. So you this electromagnetic wave, you have these two waves. You have electrical one and the magnetism. They both increase and decrease, right? So they are in two planes, which is shown in this diagram, and the propagation is along perpendicular to the two. So one is oscillating in one plane, the other one is oscillating in the other, and the electromagnetic wave propagates in the third one. So the electric field is the blue arrows, oscillates in the x plus minus direction, right? And y direction you have the electric field, and along the z, what we have here is the propagation of the right. And here is a table which shows you the color of different lights: violet, which is the limit of the human eye, and red, which is the other limit. We are between 400 to 700 nanometers, and you will see how the wavelength changes from red to violet, 700, 650, 600, orange, yellow, 540. Actually, not specifically at 580, but there's a band, it's 575 to 585 and so on. Green, cyan, blue, and violet. And this is the frequency of these in hertz, 10 to the power of 14, it's 4.29 10 to the power of 14 hertz, and so on. And you have the energy, and you see that energy is increasing as you go from red to blue and violet, right? Violet, blue are high energy ones. So this is what we have here. So because of different wavelengths, different energies, as a white beam, which is made up of all these components, goes from a rarer medium to a denser medium. The different wavelengths, they get scattered by greater amount. Their speeds in this medium changes by different amounts. The red one gets a wavelength, which is the largest wavelength, gets scattered the least. So it's almost continuing in the same direction, while the blue one gets scattered the most and it comes out. So this is something called Rayleigh scattering too, and you see that's why we see the sky as blue, because as the sunlight coming into our atmosphere gets scattered by the particles around, the blue light gets scattered the most, and hence giving the blue color to the sky, right? So the works of Raman too showed why the sea looks blue or green and why the sky blue, which we have got the Raman scattering too. And here we have the diffraction grating, which I showed here, which does the same thing, how it scatters light differently. Okay, so coming to our astronomy, you see the stars are of different sizes, different colors, and they have different colors because they are at different temperatures. And the temperature of the star tells you, the color of the star tells you essentially what is the temperature of the star. And by looking at the spectra of these stars, we can make a lot of estimates of it. We can see the temperature of the star, we can talk about the chemical composition of the star, and so on. I think I'm running out of time, so I will come through to this, which shows this is the spectra of a star, and you see some dark lines in that. And each dark line which comes at a specific wavelength tells you what is the chemical element there. So this is a sodium line. So what happens is, if sodium is present in the atmosphere of stars, or in the region between the light coming from the object to us, then these sodium atoms get excited and they absorb certain energies, and hence you get a dark band coming at that. Similarly, you have ferrous lines, you have titanium oxide lines, and different lines. So by looking at these different lines and the strength of the line, we can talk about the chemical composition of the objects. So it tells you the temperature and the chemical composition. And you put stars on according to their temperatures, and you get something called the Hertzsprung-Russell diagram. And this also tells us a lot about stars, and it tells us what is happening in the stars and how they are. Similarly, by looking at the spectra of galaxies, Hubble could study that these galaxies are moving away from us, and which gave us the understanding that the universe is expanding. So light has played a very important role in us, not only to understand, that's the only connect between us and the universe, and has given us tremendous amount of information and understanding of the whole universe. So with this, I will come to an end and take questions if there are any. Thank you. Are there any questions? Okay, if there aren't any, then we will stop for a short break and come back with the demonstrations at 11:30 sharp.